Okay, today we will look at the question paper which was based on gravitation and space mission. So let's go directly to the question paper. If you look at question number 1A, it is acceleration due to gravity decreases with the depth. That means as you go inside the surface of the earth and approach the center of the earth, the value of the acceleration due to gravity becomes, or it approaches, zero. If you just recall the formula that we use for finding the acceleration due to gravity at some depth inside the surface of the earth, then it comes out to be g m dash upon r minus h, or d rather. So what does it mean? This m dash is basically the mass of the earth, which has to be considered, in this particular case, because as we approach towards the center of the earth, the mass of the earth which is above us has to be excluded from this computation, and therefore the acceleration due to gravity decreases with the depth. Okay, let's go to the question number 2. In the same question number 1, sub question 2. So it says the initial velocity of the Mangalyaan must be greater than escape velocity of the earth. It must be greater than escape velocity of the earth. Now why it is so? It's very simple. If you look at the mission, Mangalyaan was about sending a spacecraft to the Mars, and that means for that purpose the spacecraft or the rocket had to overcome the gravitational influence of the earth, and for that to happen the initial velocity, that is the launching velocity, must be in excess of the escape velocity of the earth. That's why the answer comes out to be escape velocity. Let's move to question number 1b now. So if you look at question number 1b, it says when the planet comes nearer the sun, it moves faster, or it moves fast, or in other words we say its linear velocity increases. Now why it is so? It's very simple. Let's consider that this is the star and this is the orbit around the star, and by Kepler's first law the orbit must be elliptical in nature. Let's say this is the planet which is revolving around the star. Now what happens, as the orbit is elliptical, when the planet comes nearer the sun, it has to maintain its aerial velocity. It has to maintain or it has to cover the same area. Okay, the line that joins the planet and the sun or the star sweeps equal area in equal interval of time. That is Kepler's second law. So by that law, when the planet comes near the sun or near the star, it has to cover the same amount of area, and for that to happen, it has to cover a larger distance in the same time, and for that reason its linear speed must increase, and therefore we say that as it approaches the sun it becomes faster. Sub question 2 now. The period of a satellite in a circular orbit of radius r is t. The period of another satellite in the circular orbit of radius 4r is. Now this is based on Kepler's third law. What is Kepler's third law? Kepler's third law says that the square of the period of revolution is directly proportional to cube of the mean distance of the planet from the star. That means t square upon r cube is constant. Okay, now what happens if this radius becomes 4r? Then what we can say that t square upon r cube is equal to t dash square. That is the new period of revolution when the radius of the orbit becomes 4 times its original radius, that is 4r, divided by, it will be 4r whole cube. Now if we simplify this, it will become t square upon r cube is equal to t dash square divided by 4 cube will be 64 and r cube. Okay, now this r cube and this r cube will get cancelled, and therefore what we are left with is t dash square is equal to 64 t square. Now if we take square root on both sides, we shall get t dash is equal to 8t. Okay, that's why the correct answer in this case is 8t. Okay, let's move to the third sub question 3. It says if r represents the radius of the orbit of a satellite of mass m moving around a planet of mass m, capital M, the velocity of the satellite is given by. Now we know that when a planet is revolving around the star, suppose this is the star we are talking about, and if this is the orbit, then the satellite always has its velocity in tangential direction. So this is the tangential velocity, or we can say critical velocity, and the critical velocity always happens to be v is equal to square root of gm upon r, if r is of course the radius of the orbit. Okay, so that's the correct answer. Let's move towards the next question. Now it is question number 2. Solve the following sub questions. So first sub question in question number 2. Let the period of revolution of a planet at a distance r from a star be t, capital T, and prove that if it was at a distance of 2r from the star, its period of revolution will be root 8t. So this is what we have got to prove. Okay. Now, when the distance of a planet from the star is r, then its period of revolution is t. So that means, again by Kepler's third law, we can say clearly that t square upon r cube will be constant. Okay. Now what has happened? The new radius of the orbit has become 2r. So it has become twice its original. And if the period of the radius is going to change to 2r, then quite obviously its period of revolution will also change accordingly. Because anyhow, the ratio of square of period of revolution to cube of mean distance of the planet or radius of the planet should remain constant. And therefore we can say that if t dash is the new period of revolution, then we can say this t dash square upon 2r whole square is also going to remain constant. So again, if we simplify this, we should get that t dash square upon, this will become, this should be cube actually, 2r whole cube. So it becomes 8r cube is equal to t square upon r cube. So again, this r cube and this r cube will get cancelled, and therefore we are left with t dash square is equal to 8t square, and that means taking square roots now, t dash will be equal to root 8t. Okay, that's the answer we are looking for. Let's go to next question, that is sub question 2. This question says, why are geostationary satellites not useful for studies of polar regions? Okay, now for that, let me draw a diagram so that you can understand. Suppose this is the Earth and this is the axis of the Earth around which it rotates, and this is the equator. Okay, so geostationary satellites have the orbits which goes over its equatorial region like this. So this is the orbit. Okay, this is the orbit of geostationary satellite, and they go exactly above the equator of the Earth, and that means the satellite will not be accessible to the objects or to the regions, okay, which are extreme polar. This is the polar region. You can see this is polar region. Similarly, this is also a polar region, and this polar region do not have the access to the satellites when they are geostationary. That means they are in the orbits which go over the equatorial region, and as a result of that, the satellites are not useful to these regions. Okay, and that is why we say that if you want to study polar regions, these satellites are not going to be of any use. Let's go to next question. Now this is question 3. Force of gravitation acts on all objects proportional to their weight. Why then a heavy object does not fall faster than the light object? Okay, now for this we have to understand that this acceleration due to gravity, okay, is given by the formula gm upon r square. Okay, where capital G is obviously a constant, universal gravitational constant. Capital M is mass of the earth, or for that matter mass of any other planet, and r is the radius. Now what happens here, that the mass of the objects which are in free fall are not considered into this, and that means the value of this acceleration due to gravity, okay, will be calculated only on the basis of this constant, universal constant, mass of the planet, and of course the radius of the planet. There is no other physical quantity that is taken into consideration. There is another reason or another way to explain the same thing, that when objects are in free fall, their acceleration remains constant. Their initial velocities and their masses may be different, but irrespective of their masses and initial velocities, obviously their acceleration due to gravity remains same. And to justify this, we have to take into consideration Newton's second law of motion, which says F is equal to m into a. Now, by this formula, we know that acceleration is directly proportional to force, but at the same time, acceleration is inversely proportional to mass of the falling object in this case. So when we say that if there are two objects, one is lighter and one is heavier, then quite obviously the gravitational force acts on the larger object will be larger, and on smaller object or lighter object will be lesser. But at the same time, the acceleration is inversely proportional to the mass. So the object which is heavier experiences that much lesser acceleration, and the object which is lighter experiences that much greater acceleration. And as a result of that, actually the acceleration due to gravity is independent of the mass of the falling object. Okay, let's go to the next question. Now this is about question number 3. That is the last question. Solve the following sub questions, any two of this. So the first sub question is write 3 Kepler's law. Now the first Kepler law is very straightforward and simple. It says that the planets are revolving around the sun or stars in elliptical orbit with sun at one of the foci. So, okay, so this is what Kepler's first law is represented using the diagram, that the orbits of the planets and satellites are elliptical and not the circle as it used to be understood or perceived earlier. Let's go to Kepler's second law. The Kepler's second law talks about that the line that joins the star and the planet, okay, sweeps equal area in equal interval of time. Suppose this planet is at position A right now. In time t, in time interval t, suppose it goes to this position, let's call it as position B. So now what happens? The line that joins the planet and the star is going to sweep this much area in interval t. Now what Kepler's second law say, that wherever in the orbit the position of the planet may be, it always covers or it always sweeps equal area in equal interval of time. That means suppose the planet comes somewhere here now, let's call this as position C. So again in time interval t, same as the earlier, we are taking the same time interval. The planet will now come to position D somewhere here, so that it will again sweep the same amount of area as it swept in the earlier occasion. So that is what we say, that it sweeps the equal area, or in other words we say aerial velocity is constant. Now Kepler's third law. Kepler's third law talks about the relationship between period of revolution of planets, that is the amount of time they take to complete one revolution around the star, and it is represented by capital T. And at the same time, it relates this period of revolution to the mean distance of the planet from the star, or we can also call it as a radius of the orbit, and it is represented by R. It's a radius or mean distance of the orbit of the planet. So the relationship between these two is that the square of period of revolution, that is T square, is directly proportional to cube of the mean distance of the planet from the star. And that means the ratio of this T square and R cube is always going to remain constant. So that is Kepler's third law for you. Sub question 2 now. What is acceleration due to gravity? A bag of sugar weighs W at some place on the equator. If this bag is taken to Antarctica, okay, that means from equator, it is being taken to Antarctica, that means to polar region. Will it weigh same, more or less? Give a reason for your answer. Now let's look at the answers of this question one by one. The first part of the question is, what is acceleration due to gravity? Now, acceleration due to gravity is nothing but the acceleration that the objects in free fall experience due to the gravitational force. It is the acceleration that the bodies in free fall near the surface of the earth experience due to the gravitational force acting on them. Okay, now let's look at the second part of the question, okay, which talks about what happens to the weight. Now for that, let's draw a simple drawing. Again, if we believe that this is the earth and this is the polar region and this one is equator, okay, this is equator and this is, of course, this is North Pole and this one is, of course, South Pole. Now Antarctica means it is towards the southern pole, South Pole of the earth. So we know that the acceleration due to gravity, that is this G, changes with the altitude, and at the same time it changes with the latitude. So as you move from equator to pole, the value of this acceleration due to gravity increases, because the formula of this is Gm upon R. This is the formula for acceleration due to gravity. Now what happens as you move from equator to pole? Okay, from equator to pole, the value of radius decreases. And this is because we know that the earth is little flattened at the poles. And because it is little flattened at the poles, the radius of the earth towards the polar region is little less than its radius towards the equator. And as a result of that, the value of this acceleration due to gravity at the pole is little greater than the value of acceleration due to gravity at equator. Now coming to weight, we know that weight is given by product of mass and acceleration due to gravity. Now since the acceleration due to gravity at pole is greater, therefore the weight of any object at the pole will also be greater than the weight at the equator. That's it. Let's go to the next question, which is sub question 3. It says define weight, and then there is a numerical. How much would a 70 kilogram man weigh on the moon? What will be his mass on the earth and the moon? It is given that the value of acceleration due to gravity on moon is 1.7 meter per second square. Okay, it should be 1.7 meter per second square. Now, first of all, what is weight? What is the definition of the weight? So basically, weight of an object is defined as the force with which the earth attracts the object. So it is the gravitational force of attraction experienced by the objects because of the Earth's gravitational pull. Now, let's come to the second part of the question, that it is given that the mass of the person, that is M, is 70 kg. This is given. And we know that mass does not change with the location. Mass does not change with location. So anywhere you change your position in the universe, mass is not going to change. So whether you are on the Earth or you are on the moon, the mass is going to remain 70 kilograms. There is no change in the mass with changing location. Now, what about the weight? Now, we know that weight is again product of mass into acceleration due to gravity. It is product of mass and acceleration due to gravity. Now, acceleration due to gravity on the moon happens to be 1.7. And that means the weight on the moon will be equal to mass, that is 70 kilogram, multiplied by 1.7, that is the acceleration due to gravity on the moon. And this comes out to be around 119 newtons. That means weight of that object on the moon happens to be 119 newtons. Though it is not asked, but if at all we want to find out what will be its weight on the Earth, then it can be calculated like this. Weight on the Earth will be equal to, again, mass into acceleration due to gravity on Earth. So it will be 70 kilogram as mass remains the same, and it will be multiplied with 9.8. That is the value of acceleration due to gravity on the moon. And whatever is this product is the final answer. But in this particular question, we are supposed to calculate only weight on the moon, and it comes out to be 119 newtons. That's it.